In this video, we'll discuss the principles of evaporation technique, which is a specific method for depositing various thin film materials. In an earlier video, we explained that the fabrication process of microchips is an iterative process. Successive layers are deposited, patterned, and etched to form the complex stacked structures that provide the desired functionality. In this video, we'll discuss material deposition techniques. To illustrate the concept, let us briefly revisit the fabrication process of a quantum microchip, which we discussed in an earlier video. The fabrication process of this microchip requires the addition of materials at different stages of the process. For example, the initial step involves the deposition of niobium, aluminum, and alumina with different thicknesses. In later steps, other layers are deposited, such as silicon dioxides, to form spacer regions and niobium to form a capping layer. This example illustrates two main points. The first point relates to the thickness of these layers. Specifically, these layers have nanometer scale thickness and as such are referred to as thin films. The second point is the diversity of the deposition techniques such as evaporation as well as plasma-enhanced chemical vapor deposition techniques, which are utilized for producing different thin film materials at different stages of the fabrication process. Considering the diversity of the material deposition methods, one way to classify them is in terms of their deposition temperature range. This table here shows a simplified thermal classification of layers deposited from high temperature to low temperature. The top 5 rows are processes that involve chemical reactions among gas precursors, such as chemical vapor deposition, low pressure chemical vapor deposition, metal organic chemical vapor deposition, and plasma enhanced chemical vapor deposition and atomic layer deposition. The last 3 rows, however, are deposition techniques that are typically performed at lower temperatures. Note that the thermal classification shown in this table is an approximate with many exceptions. In particular, deposition systems can be designed and configured to accommodate a different wider temperature range. In this video, we'll focus on the evaporation technique. Evaporation is used widely, particularly in research settings, for fabricating various electronic devices. The main reasons for popularity of the evaporation method include the ease of operation, as well as the ability to produce high purity thin films due to the use of high vacuum chambers. Furthermore, evaporation is a versatile technique which can be used for evaporating diverse materials such as metals and oxides. Let us now focus on the process of evaporation. Evaporation involves the phase transformation of a material from liquid to gas. Therefore, the evaporation of solids requires them to melt first, followed by their conversion to vapor. A prime example of this process in nature involves the transformation of water to vapor upon boiling. Note that vapor can also be generated directly from solids. This process is known as sublimation. However, sublimation is not utilized in microfabrication for depositing thin films. The evaporation rate of a material under a certain condition can be quantified by vapor pressure. Vapor pressure represents the pressure of a vapor in thermodynamic equilibrium with its condensed phase in a closed system. For example, a material with low vapor pressure has lower tendency to transform into the vapor phase. In contrast, higher vapor pressure indicates greater tendency for higher evaporation rates. The plot here shows the vapor pressure of several metals versus temperature. We can make two main observations from this plot. First, as expected, the vapor pressure increases with increasing the temperature. Second, some metals need higher temperatures than others to achieve the same vapor pressure. This means some metals evaporate more easily than others. For example, while silver requires about 1000 degrees Celsius to achieve millitore range of vapor pressure, platinum, on the other hand, requires about 2000 degrees Celsius for achieving a similar vapor pressure. Besides vapor pressure, another important metric in evaporation is the deposition purity. This metric determines the specifications for both the starting material as well as the vacuum chamber. Naturally, the purity of the deposited thin film tracks the purity of the initial material. The semiconductor grade materials typically require 4/9 purity or better. Furthermore, the quality of the vacuum system affects the purity of the deposited material. As we discussed in an earlier video, the vacuum level is an indicator of the amount of residual gas molecules, such as oxygen, in a chamber. Therefore, the use of high vacuum and ultra-high vacuum systems will improve the purity of the deposited systems and materials. However, achieving these vacuum levels requires a specific pumping systems. Please review our earlier video on this topic for details on relevant pumping systems. With this background, an evaporation system consists of two main parts. First, a vacuum system to ensure the purity of the deposited material. Second, a heating mechanism for melting solids and generating vapor from the melt. Here is a simplified diagram of an evaporation system. The pumping system provides a target vacuum level in the deposition chamber, which is the enclosure in which the evaporation occurs. The heating component vaporizes the target material, which is being held in a crucible liner. A sample holder that holds wafers is positioned at a certain distance from the material source. As we'll explain later in this video, this distance affects the rate of deposition. The evaporation systems can be classified based on the mechanism by which they melt a solid source for generating the vapor. These include thermal evaporation, where a resistive heater generates heat, and e-beam evaporation, where an electron beam source is used to melt the target material. In the thermal evaporation technique, a source material is melted through Joule heating. The photograph on the left shows gold pellets that are positioned on a tungsten boat. During evaporation, an electric current is passed through the tungsten boat, which generates sufficient heat due to the boat's electrical resistance. The photograph on the right shows the boat glowing from the heat. Note that tungsten, in this case, is a suitable material choice for a boat in order to evaporate gold pellets, because tungsten requires about 2000 degrees Celsius higher temperature than gold to provide a millitore range vapor pressure. Therefore, during the evaporation of gold, very little tungsten will be evaporated, almost very negligibly. However, this example illustrates the potential competition between the boat material and the target material, which can be detrimental to achieving high purity. Therefore, thermal evaporation is an appropriate technique for depositing materials that require relatively low temperature to produce a milliton range vapor pressure. Examples of such materials include gold, silver, and aluminum. Electron beam evaporation, however, is an alternative to thermal evaporation. Specifically, this technique uses a focused beam of electrons to melt a target material locally. Because of its operating mechanism, the electron beam evaporation provides two advantages over the thermal evaporation. First, it extends the range of target materials that can be deposited. Second, it provides higher purity due to local melting of target materials. To perform this process, the target materials are placed inside a crucible liner made of a carefully chosen material to minimize cross-contamination. The crucible liner is then placed inside an evaporation pocket that permits the electron beam to access the crucible. The electron beam is generated by cathode filament, and this beam is then focused and guided by magnetic field to melt the target material inside the crucible liner. Let us now discuss the deposition rate. To control the film thickness and spatial uniformity across a sample, it is important to examine the factors that influence the deposition rate. The deposition rate, nu, depends on the source evaporation rate, or evap, the density of the target material, n, the throw distance, r, and the theta k, which is the angle between the surface normal and the direction of the source. The source evaporation rate is determined by the vapor pressure of the target material at a given temperature. The throw distance r and theta k are determined by the distance between the wafer holder and the point source, which is denoted as h here. Using the equation here and assuming a fixed source evaporation rate, or evap, we can plot the deposition rate as a function of the position of the spot on a wafer. The deposition rate here in this plot is normalized relative to the rate at the center of the wafer. An important observation from this analysis is that the deposition rate decreases as the distance from the surface of the wafer increases. This variation in the deposition rate leads to an uneven film thickness across the wafer, which is an undesirable effect. Therefore, it is important to determine the length scale at which the thickness across a wafer is uniform. Using this plot and assuming h equal to 13 inches, 95% thickness uniformity can be achieved across a 3-inch diameter wafer. While evaporation is a simple and versatile technique, it is important to be aware of its limitations when designing a fabrication process. A crucial limitation of evaporation is in achieving a complete step coverage, which is to provide a uniform film thickness on structures with topographic steps. This limitation arises from the directionality of the evaporation process. Alternative deposition techniques, such as chemical vapor deposition or sputtering, offer significantly better step coverage than evaporation. In summary, evaporation is used extensively in research settings due to its versatility for depositing various thin film materials and ability to produce high purity films. However, this technique often falls short of depositing low vapor deposition materials such as tungsten or processes requiring complete step coverage. Therefore, alternative approaches such as CVD and sputtering are used to address these shortcomings.